So what is buffer solution? Buffer solutions maintain a stable pH by neutralizing acid and bases. A buffer solution consists of a weak acid and conjugate base which exchange protons and hydroxide ions to form water. So, in simple words, ang buffer solution is ang gahelp siya og maintain sa kanang stable sa pH by kanang pag-neutralize sa acid and bases. And ang buffer solution consists of weak acid and conjugate base. Ga-exchange ang protons of hydroxide ions to form water. So, one way to determine the pH of a buffer is to use the Henderson-Hasselbalch equation. So, what is Henderson-Hasselbalch equation? So, the Henderson-Hasselbalch equation expresses the pH as a function of the pK and the ratio of base and acid concentration. So, here's a video gikan sa Khan Academy for more elaboration of a buffer solution and the use of Henderson-Hasselbalch equation.
Buffer solutions resist changes in pH, and so let's think about a solution of a weak acid and its conjugate base. So here we have HA, which is our generic weak acid, and so the conjugate base would be A-. And a buffer solution needs to have substantial amounts of both present, and that's what I'm trying to represent over here. So we have a beaker, right, that has in this case equal amounts of HA and A-. And to our buffer solution, we're going to add some strong acid, so a source of protons. So I'm going to draw a proton in here, so H+. I could have written H3O+, because H+ and H2O give you H3O+. I'm just writing H+ to make it a little bit easier to think about. So if you're increasing the concentration of H+ ions, or you're increasing the concentration of hydronium ions in solution, you would think that would decrease the pH dramatically. And that would happen if you didn't have something to react with the protons in solution. But we do in our buffer solution, right? We have A-, we have our base. The base is going to pick up this proton, and H+ and A- are going to form HA. So we're going to make more of our weak acid here. So let's see, we started out with some weak acids. Let me go ahead and draw that in here. So some HA. And then we're going to make more because H+ and A- give us HA. So we're making more of our weak acid here. What about A-? All right, well, we're going to use one of these up to make HA, right? So now we have only two of these left. So we're decreasing the concentration of A-. But what we've done is we've effectively removed protons from solution, and that's how a buffer is able to resist a change in pH if you add acid. What about if you add base? So next, let's think about our buffer solution. And this time we're going to add a strong base. So we're going to increase the concentration of hydroxide ions in solution. So if we increase the concentration of hydroxide ions in solution, you would think that would increase the pH, right? And it would, except for the fact that we have an acid that can react with our base, right? So we have some weak acid present here, and the hydroxide ion is going to pick up a proton from HA, right? So we have H+ here. So OH- and H+ give us H2O. So we're going to make water here. Right, so we're going to lose some of our weak acid. So we started with 3, and now we have only 2 left here. And if OH-, if hydroxide takes a proton away from HA, then we're left with A-. So we're going to increase the amount of A- that we have, right, in solution. So let me go ahead and draw that in here. So once again, we've effectively buffered against a change in pH because the hydroxide ions that we added, right, were reacted with the acid that was present. So we've effectively removed hydroxide ions from solution. All right, so that's the idea of a buffer solution. Let's see if we can derive an equation that will allow us to do some calculations. And so next, let's look at what we have down here. Right, so we know that we have in a buffer we have substantial amounts of HA and A- present, and so we have this reaction at equilibrium. So for our equilibrium expression, right, concentration of products over concentration of reactants. So here we have our concentration of products over our concentration of reactants, once again leaving water out. let's take the negative log of both sides of this. So we're going to take the negative log of Ka, so that would be negative log of Ka here, and the negative log of all of this, which would be equal to the negative log of all of that. And I'm going to write it a little bit differently. I'm going to put the concentration of hydronium ions out front here, and then have concentration of A minus over concentration of HA. Alright, I wrote it like this because it makes it a little bit easier to see a property of a logarithm. Let me just go ahead and write down the property that I'm referring to. If you have log of A times B, that's the same thing as log of A plus log of B. And here we have the negative log. So the negative log of AB is equal to the negative log of A plus the negative log of B. So I'm just going to write minus the log of B here. And in this case, right, concentration of H3O plus, that would be A. Right? So this would be A, and then this over here would be B. Right? So let's think about what that would give us now. So let's get some more space, and let's think about our log property. So on the left side, we have negative log of Ka, and the right side, we would have negative log of A, so that would be negative log of concentration of H3O plus, right, minus the log of B here. So that would be minus the log, and B was this right here, minus the log of A minus over HA. Alright, so we can keep going here, because we know the negative log of Ka, right, the negative log of Ka is equal to the pKa. So this is equal to the pKa. And then over here we have the negative log of the concentration of hydronium ions. That's equal to the pH, right? So negative log of concentration of H3O plus is equal to the pH. And then we have minus log of the concentration of A minus over the concentration of HA. And so we can rewrite this in for our final equation. So we're just going to rewrite this, solve for pH. pH is equal to pKa plus the log of A minus over the concentration of HA here. And this is called the Henderson-Hasselbalch equation. So right here is the Henderson-Hasselbalch equation. It's very useful when you're doing buffer calculations. All right, we'll look at examples of this in the next video.
So let's do some buffer solution calculation using the Henderson-Hasselbalch equation. So, mao ni ang given nga problem. What is the pH of a buffer solution that is 0.24 mole Na and 0.20 mole NH4Cl? So, diba ang formula is pH equal to pKa plus log of the conjugate A minus over the conjugate of HA. So, we're talking about the conjugate acid-base pair here, the HA and A minus. And for our problem HA, the acid would be NH4 plus and the base would be NH3 or ammonia. So, una na to buhaton is i-calculate na to ang pH sa buffer solution. So, let's say kabalo na ta sa Ka value sa NH4 plus. Ka is equal to 5.6 times 10 to the exponent of negative 10. So, para makuha na to ang pKa, all we have to do is to take the negative log of that. So, pKa equals the negative log of 5.6 times 10 to the exponent of 10. O, makuha na tag calculator para itong isolve. So magkuha tag calculator para itong isolve. So, negative log 5.6 times 10 to the exponent of negative 10. So, mag-result siya og 9.25. Kuha na nato ang pKa which is ang 9.25. So, pwede na ito makuha ayahang pH. pH is equal to pKa plus log of the conjugate of A minus over the conjugate of HA. pH is equal to 9.5 plus log of the conjugate of 0.24 over 0.20. So, i-calculate na ito siya para makuha na ito ang pH. Pag humana ito, solve ito, nakuha na ito ang 0.08. So 9.5 plus 0.8 is equal to 9.33. So, the final pH of our buffer solution is 9.33. So, dapat hinumduman yun nga number sa pH kaya we are going to compare what happens to the pH when you add some acid and when you add some base. Kaya ang next problem na to is adding base to our buffer solution nga i-discuss ni Jordan.
So, good afternoon everyone. My name is Jobin B. Jamali and I will be the one who give an example of Henderson-Hasselbalch under sa adaptive learning nga Khan Academy. So let's start. So natay question dire, problem question. If 0.005 mole of NaOH is added to 0.50 liters of the buffer solution, which is ang 0.24 molar of NH3 and 0.20 molar of NH4Cl. So ang question is, what is the resulting pH? So first is, before ta mag-proceed, you can pause the video o mag-advance mo answer. Kamu na'y bahala na. So, alright. So first step is, atong i-calculate ang pKa. So let's assume nga na ay Ka o ang value sa Ka is 5.6 times 10 to the power of negative 10. Ato na siya i-calculate negative log times sa 5.6 times 10 to the power of negative 10. So i-try ninyo guys. Kung ang iyang value is 9.25. So natay value sa pKa 9.25. Katawa po. Ay katawa. So let's proceed sa conversion sa mole, sa molar, sa mole o sa liters. So na ay 0.005 mole divided by 0.50 liters. Ang mole. So ang value is 0.01. So since na natay value sa hydroxide which is ang 0.01, let's proceed sa reaction. So naay natay NH4 which is ang ammonium, NH4 plus OH which is ang hydroxide, negative OH hydroxide. Ilang value sa NH4? 0.20 molar. 20 molar. O sa negative OH, ang 0.01. 0.01. So sa PCAS, if ang reaction, after sa reaction, mag-donate ang NH4 or ang ammonium o proton, mahimo siya og H2O which is ang water plus NH3. Na-value ang NH3 which is ang 0.20 NH3 0.24 24 molar. So manisa guys. So after sa reaction ng duwa sa NH4 plus o OH which is ang hydroxide, makuhaan ni sila og particles o tagsa-tagsa. Kuhaan ni sila particles negative 0.01. same sa other side, 0. Sa OH, 0.01, 0.19. So mabili nilang sa NH4 is 0.19, sa OH is 0. While ga malus sa particle diri sa reaction sa left side, ang pikas nga side is makakin siya og particles. So ang 0.24 ma-add siya og 1 plus 0.01. So may mo siya og 0.25 molar. So since na natay value sa conjugate base o sa acid, so proceed with sa equation. So ang equation sa Henderson-Hasselbalch is pH equals pKa plus log and conjugate base over acid. So pila may value sa pKa? Natay 9.25 plus log sa concentration base is 0.19. 0.19 ba? Ang iyang concentration base is 0.25 molar o ang iyang acid is 0.19. So kung ato ni substitute, ang iyang value is 9.37. So since two decimal ra atong gigamit, ang last nga digit is maato rang gi-round up. So mao to guys. Thank you.
Hey everyone, it's Saima and now let's talk about Henderson-Hasselbalch equation. Henderson-Hasselbalch equation is ginagamit siya para i-calculate ang pH of solutions with known amount of acid and conjugate base. An equation that could calculate the pH value of a given buffer solution was first derived by the American chemist Lawrence Joseph Henderson. This equation was then re-expressed in logarithmic terms by the Danish chemist Carl Albert Hasselbalch. To better understand the Henderson-Hasselbalch equation, here's a video from Khan Academy for you to watch.
The Henderson-Hasselbalch equation is an equation that's often used to calculate the pH of buffer solutions. Buffers consist of a weak acid and its conjugate base. So for a generic weak acid, we could call that HA, and therefore its conjugate base would be A-. To calculate the pH of the buffer solution, we would find the pKa of the weak acid, and to that we would add the log of the concentration of the conjugate base divided by the concentration of the base, the acetate anion. And let's use this particulate diagram to help us calculate the pH of the buffer solution. Remember that the goal of a particulate diagram is not to represent every particle in the solution, but to give us an idea about what's going on in the entire solution. And also, when looking at the particulate diagrams of buffer solutions, water molecules and cations are often left out for clarity. Let's count the number of particles of acetic acid in our particulate diagram. So in our diagram, there are 5 particles of acetic acid, and for the acetate anion, there are also 5. Because there are 5 particles of both acetic acid and the acetate anion, the concentration of acetic acid is equal to the concentration of the acetate anion. Next, let's think about the Henderson-Hasselbalch equation. Our goal is to calculate the pH of this buffer solution represented in the particulate diagram. And so first, we need to know the pKa of the weak acid, which is acetic acid. At 25 degrees Celsius, the Ka value for acetic acid is equal to 1.8 times 10 to the negative 5th. The Ka value is less than 1 because acetic acid is a weak acid. To find the pKa of acetic acid, we take the negative log of the Ka value. So the negative log of 1.8 times 10 to the negative 5th is equal to 4.74. So we can go back to the Henderson-Hasselbalch equation and write that the pH is equal to the pKa, which we just calculated to be 4.74, plus the log of the concentration of the conjugate base. And the conjugate base is the acetate anion, so let's write that in here, CH3COO minus, and that's divided by the concentration of the weak acid, which is acetic acid, CH3COOH. We've already figured out that the concentration of acetic acid is equal to the concentration of the acetate anion. Therefore, the concentration of the acetate anion divided by the concentration of acetic acid is just equal to 1, and the log of 1 is equal to 0. So let's go ahead and write that in here. The log of 1 is equal to 0. Therefore, the pH of the buffer solution is equal to 4.74 plus 0, or just 4.74. So whenever the concentration of the weak acid is equal to the concentration of the conjugate base, the pH of the buffer solution is equal to the pKa of the weak acid. Let's look at another particulate diagram. We still have an acetic acid acetate buffer solution. However, this is a different buffer solution than the previous problem. So let's count our particles. For acetic acid, there are 6 particles, and for the acetate anion, there are only 4. Since we have more acetic acid particles than acetate particles, the concentration of acetic acid is greater than the concentration of the acetate anion. We can use the Henderson-Hasselbalch equation to think about the pH of this buffer solution. So the pH is equal to the pKa, which we calculated in the previous problem for acetic acid. It's 4.74 at 25 degrees Celsius, plus the log of the concentration of the acetate anion divided by the concentration of acetic acid. In this case, the concentration of acetic acid is greater than the concentration of the acetate anion. Therefore, we have a smaller concentration divided by a larger concentration. So we have a number less than 1. And the log of a number less than 1 is negative. Therefore, all of this would be negative or less than 0. So we would be subtracting a number from 4.74. Therefore, we can say the pH of the solution would be less than 4.74. Let's do one more particulate diagram of an acetic acid acetate buffer solution. Once again, we count our particles. So for acetic acid, this time there are 4 particles, and for the acetate anion, this time there are 6 particles. Since we have only 4 particles of acetic acid and 6 particles of the acetate anion, the concentration of acetic acid is less than the concentration of the acetate anion. Or we could say the concentration of the acetate anion is greater than the concentration of acetic acid. Thinking about the Henderson-Hasselbalch equation, once again the pKa is equal to 4.74, and we need to think about the ratio of the concentration of the acetate anion to the concentration of acetic acid. For this example, the concentration of the acetate anion is greater than the concentration of acetic acid. Therefore, the ratio would be greater than 1, and the log of a number greater than 1 is positive or greater than 0. Therefore, we would be adding a number to 4.74. So for this buffer solution, the pH would be greater than 4.74. Finally, let's summarize what we've learned from our 3 different particulate diagrams. In the first example, the concentration of the weak acid was equal to the concentration of the conjugate base, and therefore the pH of the buffer solution was equal to the pKa of the weak acid. In the second example, the concentration of the weak acid was greater than the concentration of the conjugate base, and therefore the pH of the buffer solution is less than the pKa of the weak acid. And in the third example, the concentration of the weak acid was less than the concentration of the conjugate base. Therefore, the pH of the buffer solution was greater than the pKa of the weak acid. So if we know the pH of a buffer solution, we can think about the Henderson-Hasselbalch equation to think about the relative concentrations of the weak acid and the conjugate base. For example, if we have a particular buffer solution and we know the pH of the buffer solution is less than the pK of the weak acid, we know that in that buffer at that moment in time, the concentration of the weak acid is greater than the concentration of the conjugate base.